So we're going to look at repeated sampling and the central limit theorem. So this is combining a bit of the stuff that we've looked at so far. We've looked at sampling and why we sample and what's the goal behind sampling. So when we sample, what are we trying to find out?
Representation of population.
We're trying to find something out about a population. Why do we sample not? We can put our laptops down, we are listening. You get a chance to do your laptops later. Why do we sample over just asking everyone? A lot quicker, a lot easier, a lot quicker. Depending on the size of the population, it might even be impossible. What's some of the problems that we have when we're doing sampling? Bias. So that's when the sample we select doesn't represent the population. Yes. Non-response and all those sort of things, okay? But bias encaptures non-response, response and undercoverage, okay? So it represents all of those, but essentially bias is when our sample doesn't represent our population. So providing we've got a random sample and it represents our population, there's no bias, we can do certain things that allow us to be much more confident in our data collection. Much more confident and make assessments about what's actually going on within that population. And we use this thing called the central limit theorem. Now the central limit theorem essentially says if we collect a bunch of random samples, providing we've got enough samples, a big enough n value, then we can apply a normal approximation. And that works regardless of the parent population. So regardless of whether my parent population is a normal distribution, a constant distribution, a parabolic distribution. So my parent population could look like this. It could look, so that's my parent population, it could look like this. It could look like this. It doesn't matter what it looks like. What will happen when I collect the means, so if I collect the means, I'll get a heap of values around here. If I did lots of repeated samples, I'd get a heap of values there, right? Does that make sense? If I did heaps of samples of that population. Are we good with that? If I had like 60 people from each group. The same thing would happen here. Like I'd be collecting data and most of my data would fall in the middle. It would be a little bit wider, but it still would be around the middle, correct? The normal distribution. Does that make sense what I'm saying? So this represents every individual. If I collected a group of 60 individuals, I would expect the average of their weight to sit in the middle and then slowly go out. Do you think that with these distributions I'm going to get a larger variance or a smaller variance the same way normal distribution? I'm going to get a larger variance, but I'll still get a normal distribution, correct? Good. And that's what the central limit theorem is saying, is regardless of what my parent population looks like, I'm going to get a normal distribution when I take the averages. Are we happy with that? So do you understand what I say by repeated sampling? What is that talking about? I'm going to guess from your silence you're not fully sure. That's when I grab a group of 60 people, let's say, and ask them about which is your favourite. Do you like the Cowboys, for example? So if I ask 60 people, do you like the Cowboys? And the population proportion, instead of the population of kite, the population proportion is actually 60%. Well, if I ask the first 60 people, they give me 55% that say they like the Cowboys. The next 60 people, 65% say they like the Cowboys. The next 60 people, 48% say they like the Cowboys, etc., etc. Where is it going to centre around? Around that 60%, correct? We'd expect it to be around that 60%. Of people say they like the Cowboys. Does that make sense? So if I do lots and lots of samples, I'll get a normal distribution where the mean should be pretty close to my population mean. Is it going to be exactly the same? No, and that's where the normal distribution allows us to do a few things, a few special things. So there are some notes you need to take around this. So the population proportion is pretty close to our sample proportion is pretty close to our population proportion, which is actually P, but I'm just going to try and train you from getting confused. I put U there. Why have I put U there? I mean, we're more familiar with that. Cool. And the standard error. Now the standard error is just another way of saying the standard distribution of our new normal distribution. Cool? Why haven't I put the standard deviation of our new distribution there? Because that's the standard deviation of the old distribution. Happy with that? And that is equal to the standard divided by the number of people in the sample. So our sample size before was what? 60. So let's say my standard deviation was 5%. It would be 5% divided by the square root of 60. That'd be my new standard deviation. And that comes from the fact that the variance is equal to P1 minus P over N. Okay, that's the variance, correct? So if we square root all of that, then we get the standard deviation is equal to the normal standard deviation equation is equal to the square root of P1 minus P. So they're both the same thing. Happy with that? So we do need to remember those things. I'm just going to get rid of that so we're not getting confused. We do need to write down those three things because they are very important. So what this allows us to do is we can use our normal probability and our understanding of normal probability to say, well, let's say I've done 50 samples, right? I've done a heap of samples. I've found my mean, I've found my standard deviation. Within what range am I fairly confident of my value sitting? So how many standard deviations hold 95% of the population? 2. So if I get a parent, if I get not what I wanted, words, a sample proportion, if I get a sample proportion in that Cowboys example of 58%, so 0.58, and the standard deviation of my standard error is 0.2, how would I know what range am I 95% confident the true value of Cowboys fan sits? So I'll say that again. For the example I was talking about before, is 0.58. My sample proportion is 0.58. My standard error, which is my standard deviation of my new value, is equal to 0.02. What set of values would I expect to hold 95%, or like I'm 95% certain this is the actual value of Cowboys fans in the town? So what did you say before? How many standard deviations holds 2? 3 is 99.7%. So if I want to be absolutely certain I'd go 3, I'm probably, given the Cowboys fans who really care, it's like 95% is enough. So what could I do? What's my mean? Where do I expect? Where's my mean at right now? 0.58 plus or minus what? 0.02. Am I done there? That's one standard deviation, correct? So it's 2 times that. Are we seeing how we can use that? So then I'm 95% sure the number of Cowboys fans in Mackay is between 62% and 54% of people. I'm 95% sure of that. I only had to sample a small group of people a number of times. And I've removed all of my bias because I'm grabbing people from different sample groups, so I'm not going to get similar population traits there. Cool? Are we happy with that?
Yeah.
We're understanding where that's pretty valuable. So this ties in very, very closely to the normal distribution. And it's actually how we apply statistics. So watch that video on the dragons and the bunnies, and that'll probably